Hello everyone, I'm Graphio12 and I'll be teaching today method resolution order. It's a very important concept in object oriented programming. More specifically, it arises in languages which allow for multiple inheritances. Now, method resolution order means suppose there is a class A which inherits from say B. B inherits from C. So C is the like a grandparent, B is the parent, and A is the child class. Suppose now someone takes X to be an instance of A and tries to call a method say M. Now what the compiler on the interpreter of that language will do, it will try to search if the method exists in A or not. Naturally, if it does not exist in A, then it must have been inherited from B. So it checks in B if the definition is in B or not. If it is not in B, then it will check in C. And if it is not present, then obviously it will give an error. Now, this is straightforward, simple when there are only single inheritances. So it forms a chain. Now, what happens if there are multiple inheritances? Suppose A, it inherits from B, it also inherits from C, and B and C both inherit from a parent class called D. Now, if we are trying to call that same method x.m, x being an instance of the A class, then the interpreter will be confused. If it does not find that method in A, where will it go? To B or to C? Or if it doesn't find in B, should it go to D or call the method that is found in C? So in that case, there must be an order, an algorithm that must be followed to resolve in what order, in what search path will the interpreter try to find the methods. And that order is known as method resolution order, or MRO in short. Now, there are various ways to look for an MRO. I'll be talking about two ways. The first one is called DLR, and the second one is known as C3 Linearization. I'll be talking in perspective of Python, because both these algorithms are part of Python MRO. Now, when Python newest version was less than 2.3, what the interpreter did for MRO was it followed DLR. Now, what is the full form of DLR? It means depth first, left to right. So you see here, this is actually a directed graph. That means starting from A, we are able to do a depth first search. Okay, so if we do a depth first search, so what will be the result? If I do a DFS of this graph, then the result is going to be See, first it will go to A. Then what is the leftmost subclass of the superclass of A? It's B. So it will go B. Now it will go as much deep as possible. So it will start looking from B. So B has only one parent, that is D. So it will be D. And now A is visited, B is visited, D is visited. Now it backtracks to A and finds if there is any unvisited neighbor of A. Yes, there is an unvisited neighbor C. So it visits C and C. So how will be the search going on? Suppose we call for a method in A. So it will first look in A. If not found, it will look in B. Then if again not found, it will look in D. And if it not found, it will look in C. Now think of this. Suppose this is you. These are your parents. And these is your grandparent. Now, if you are to inherit some character or some trait or some behavior, personality, whom would you get more inspired from? It will be your parents. So, what do you think? Is the method resolution order logically correct? No, it's not. Why? Because if the solution is not found in B, then it goes to the grandparent. No, you'd better inherit your traits from your uncle than from your grandfather. So it should not be like that. So C should come before D. So that is why the concept of depth first left to right was scraped from Python 2.3 plus. So Python 2.3 plus and all of Python 3 so all of Python 2.3 plus and Python 3 follows what is known as the C3 Linearization Algorithm. Now let us look into what is the C3 Linearization Algorithm. We will consider the same class hierarchy that we considered before. The MRO or the search path for any class is also known as the linearization of the class, and we depict the linearization of a class by L of x. Suppose the class is x and its linearization will be L of x. What this algorithm tells is that the linearization of a class A will be the list A plus a unique merge of the linearization of all its parents Pi and the list of its parent. Now what does that mean? Let's check one by one. Let's go to the grandfather class D. So are there any parents of D? No. So the linearization of D will be the list D itself. Now come to B. What will be the linearization of B? It will be B and the merge of its parents linearization, that is D list and the list D. So if you merge, these are actually in fact the same, so the merge will become D itself. So the linearization will be B comma D. For C, similarly we have C comma D. Now for A, what will be for A? A will be the merge of A and the merge of the linearization of B So the linearization of B is B comma D. The linearization of C, which is C comma D, and its parents, which are B and C. Now, how to do this merge? Let's do this merge. See, check from beginning to end the head of all the lists. Take B. Does B appear as not a head in any of the list? Means it appears in the second element or third element in any other list? No. It always appears at the head. So B is a good candidate for the merge. So you write A, B, and still the merge has to be done for D taken out. We take out B from this list, so B goes here, only D is left. C comma D, and then only C. Now think, we are working on this list. Now the next element in this list is D. Check the head, this is D. Does D appear as a second element or onwards in any other list? Yes, it appears here. So we won't take D. D is not a good candidate. What is a good candidate? C. See, C is not in the second or third element plus in any of the lists. It is always at the head of the list. So we will include C. So we included A, B, C, and the merge of D, D, and nothing else. So what is remaining is D, and we will take D. So the method resolution order or the linearization of the class that we get is basically A, B, C, D. Basically is this. See, it now follows our logic that you have inherit traits from not from your grandfather but from your uncle. See, C appears before D. Now, this is a bit tedious, and C3 linearization algorithm does not always guarantee that you will find a stable method resolution order. Uh, Let me take an example to show when it can fail. Uh, I will take a difficult example first. So, say I'm writing Python code. Say there is a class O that is the parent of all classes. Then there is class A that inherits from O. Class B also inherits from O. Class C inherits from A comma B. See the order, A comma B. So A first, then B. Class D inherits from B comma A. So B first, then D. And there is a class E that inherits from C and D. Now we quickly draw the graph for this structure. This graph is also known as the diamond diagram. So write E, then we have C, then we have D, then from C we have A and B, and for D, B is the left parent, and A comes as the right parent, and both A and B inherit from O. Okay, so let us try to find out the linearization of C. So we will start from the ancestor, the greatest ancestor. So its linearization is simple, it's O. its linearization is also simple. It's a comma o. B for B, it's b comma o. Now for C it's C and the merge of AO, BO and AB. So what it is gonna be? AC, A, B, O. Now you try to do the merge of D. So for D, it's gonna be D, then B, then A, then O. Because B and A occur in reverse order in D. Now you try to do the merge of E. The linearization of E. So what will it will be? E, then merge of C A B O, D A B O and C D. Now for the merge, we see that at first that C is a good candidate, so we cross out C. So I will write it here. So I get E, then C. Then does A, it should be DBAO here, DBAO. Now we say that does A appear as the second element or third element of any list? Yeah, it appears. So A is not a good candidate. Now the next good candidate is apparently it's D. So we cross out D and place D. Now there is a catch. Should I place A or should I place B? Because if I try to select A, then it appears as the second element of this list. If I try to select B, then it appears as the second element of this list. That means there is no stable MRO found. And if you were to create this class in Python, then it would simply fail. You will see an error that there can be no stable MRO found. It will give an error. So C3 linearization algorithm does not always guarantee that you will get an MRO, but it does guarantee that the locally the inherited structures that are there will be preserved, because you will not inherit something which your uncle has from your grandfather. Now I come to a shortcut trick to find out the linearization. So it is not that much intuitive to follow these recursive definitions and one by one and compute linearization. It is too tedious. So there is a shortcut trick. What is the trick? You try to do the DFS, the DLR algorithm of the of this class. So in DLR algorithm, you just note down which vertices you have visited. So I start from A, then I visit to B, sorry, then I visit D, then I came back to B, and we do not write when we come back to some place, but we do write the vertices when we go in an upward journey. Means in this way, if we move, then we note down the vertices even if it is visited before. So we note down A, then we note down B, then we note down D, then we come back to A, then we note down C, then we note down D again. See, D was visited before, still we are noting down because obviously the algorithm will once go to D. Then scan the list from left to right and try to find, is there an element which has appeared before its children? So all the parents must appear after their child. You see that there is D who has a child class C, but it appears before C. So you cross out D. And you see ABCD is the C3 linearization that we proposed earlier. If you try to solve the linearization using that trick in this case, you will still get a result, but That is why you have to check using the actual algorithm that the stable algorithm exists or not. If it exists, then you can follow this. Thank you.